My name is Joey Watts, and I'm a software engineer at Bloomberg. I recently contributed to the TypeScript compiler, working on a large JavaScript feature. Collaborating with the TypeScript team is really fun and surprisingly easy since they work out in the open on GitHub. In this talk, I'm going to go over what the new JavaScript feature, private fields, is. Then I'm going to explain how the TypeScript compiler works. And while we go through the TypeScript compiler, we're going to explore how to implement private fields in the compiler. Private fields is currently a proposal to the ECMAScript standard. The proposal comes with a specification that precisely defines how it works. The proposal is currently in stage 3. This is the phase where we typically implement the feature in JavaScript engines and in TypeScript. To introduce you to private fields, we're going to talk about how they're similar and different from the TypeScript private keyword. In this example, we have a class person which has a name property. The two examples show the different ways to mark it as private. With the TypeScript private keyword, we use the underscore name as the name of the property. This is just a convention. And we use the private keyword to mark it as private to the compiler. So the compiler does the heavy lifting for us and checks that any code outside of this class that tries to access the name property gets an error. With ES private fields, we prefix the name of the property with a hash. This ensures that any code outside of this class cannot access this hash name. You can see that the code is very similar between the two. And a lot of the time, you'll simply need to replace a private keyword with a hash prefix. Some people say that hash is the new underscore, since underscore is the pattern that's typically used to denote a private field in JavaScript. One of the advantages of ES private fields is that you get runtime privacy. So you can't cast away to any in order to access private members of a class. You really need to have the code be within the class in order to access a hash foo property. You might be wondering how these are different. One of the main differences is that the TypeScript private keyword compiles down to a regular JavaScript property. So JavaScript consumers can easily accidentally access a private field that you didn't mean to expose in your public API. Additionally, TypeScript consumers, which cast the values to any, also can access the field unprotected. This is not the case for hash fields or the ES private fields. You get a runtime error if you attempt to access a private field outside of the current class. Earlier, I mentioned that the proposal comes with a specification that precisely defines its behavior. The specification for the entire language is called the ECMAScript specification. In this specification, we'll look at mainly 4 things when we're implementing the feature. I'll go over precisely what those 4 things are as we move through the compiler and start to understand how it works. As we go through the compiler, we'll talk about 5 different phases: the scanner, the parser, binder, checker, and transformer. Let's start by talking about the scanner. The scanner scans the source code for tokens. A token is the smallest meaningful unit of a language. In this animation, you can see that a cursor scrolling over this text and outlining the tokens with boxes. The part of the specification that defines what a token is called the lexical grammar. With private fields, we introduce a new token called a private identifier. Essentially, this is showing you that a private identifier is the same as a regular identifier. It just is prefixed with a hash. Tokens can typically not contain white space, with the exception of a string literal. The specification here is telling us that there is not allowed to be a space between the hash and the identifier name. So here's some pseudocode for us to introduce the ability to parse out private identifier tokens in the scanner. When you see a hash symbol, we should expect to see an identifier start after, or the start of an identifier, followed by anything that an identifier can contain. The reason why we have this identifier start and the identifier parts is because an identifier can start with a certain set of characters and then can contain a larger set of characters. For example, an identifier cannot start with a number, but it can contain a number. We need to expect that we see a character that an identifier can start with, followed by the rest of the identifier. When there are no more identifier parts, we set the token to private identifier. This is the actual code that we introduced into the compiler. I don't expect you to actually read all of this, but this is just to prove that we actually did introduce the code. The next phase is the parser. The parser takes these tokens that the scanner produces and turns them into an abstract syntax tree. The part of the spec that we look at when we're making changes to the parser is called the syntactic grammar. The syntactic grammar gives us a rough structure of what the abstract syntax tree might look like. It doesn't necessarily directly correspond to the syntax tree that TypeScript produces, since the names of the different nodes may be different. In the change to this spec, we see that there's a field definition being introduced to the class element. This means that classes can now contain fields. And when we look at the definition of the field definition syntactic grammar, it tells us that a field definition consists of a name and an optional initializer, and that name can be a private identifier. You may be thinking, what does this abstract syntax tree mean? Well, if you've used code features like the code folding or the breadcrumbs, we've already sort of thought about code as being in the form of a tree. TypeScript also thinks about code this way. When it's processing your code, it produces a tree, like the one shown on this slide. You can use the TypeScript AST viewer to actually show you exactly what the TypeScript AST looks like. It turns out that the AST viewer is really good for determining exactly where in the parser you should be looking to introduce a change. We can often use the AST viewer to determine where in the code in the parser we need to modify in order to add the feature that we're trying to add. So if we type some code into the TypeScript AST viewer and find a node that's somewhere close to the parsing code that we want to change. So in this case, I have a class A with a foo property. If I highlight that foo property, it'll highlight it in the syntax tree. I can use the syntax tree to find the roughly corresponding call stack in the parser. So you can see that the call stack, the functions in the parser, often correspond to the name of the nodes in the syntax tree. So we want to introduce this private identifier token, or AST node, in this location. So we'll find that parse property or method declaration function and add an if statement to check if the token is a private identifier. When we have a private identifier, we can add a private identifier node into the syntax tree under the property declaration. So the change we want to make is to insert a private identifier here. In order to do that, we just find out where we're parsing the property name in a class, and then we introduce the ability to parse out a private identifier node in that place. The next phase of the compiler is called the binder. The binder creates symbols which connect the usage of something to its declaration. Symbols also contain information about the type of a declaration. So in this example, you can see this.foo is a usage of the foo declaration of a field in the class A. The binder is important for core editor features that you would expect, like being able to hover over a declaration and see what its type is, or being able to determine if something is not being used or not. In order to implement private fields in the binder, we need to understand how the usage of a private field links back to its declaration. Each private field is distinct in scope to its class. In this example, we'll demonstrate exactly what that means. We have a class child that extends a parent class. The parent contains a hash foo property, and the child also defines a hash foo property. It turns out that these two properties are distinct, and neither class can detect each other's hash foo property. The hash foo in the child does not overwrite the hash foo in the parent. When we call log foo in the parent class, the code in that function, when it accesses hash foo, links back to the hash foo that was defined in the parent, even on a child instance. So when I call log foo with an instance of the child class, it will log from parent, not from child. It's easier to think about the scoping of private fields as being more akin to a variable declaration or lexical scoping rather than a property that is bound to an object. In order to implement private fields in the binder, we need to create symbols for the declarations. Because the private field is very much linked back to the class that which it was declared in, we need to store information about the class that it was declared in. So the name of the symbol stores the ID of the class's symbol as well. So when we have an instance of the child class, we can determine whether it has the hash foo property from the child and the hash foo property from the parent, or both. A lot of the compiler's code is moving around between nodes, symbols, and types. The binder sets up all this information, and this diagram shows us exactly how to move between these types. If we have an AST node, we can use get symbol at location to get a symbol, and then we can use get type of symbol to get the type of that symbol. Oftentimes, errors in the checker are implemented based on errors that are contained within the specification. So for example, the delete operator in the specification tells us that we can't delete a private field. This code snippet shows exactly where we inserted the check that produces an error at compile time when we try to delete a private field off of an object. We found this place to insert this code just by searching for a similar error, like trying to delete something that's not a property reference. If we try to delete a regular variable, we get an error that says the operand of a delete operator must be a property reference. We can search the codebase for exactly where this error is emitted and then produce an error in a similar location. It's important that the checker gets clear to the root of a problem. This shadowing example shows exactly how errors can be really cryptic, and it's important for us to have a descriptive error message that explains exactly what the problem is. In this example, we have a class B within a class A, and they both define the same private field. This is problematic because in class B, you can't access the hash foo from class A because class B's hash foo shadows it, much like how if you were to do this with variable declarations, the variable declarations would shadow each other. The nested variable will shadow the outer variable. If we simply said that this hash foo property from class B doesn't exist on class A, if we simply said that hash foo does not exist on the property on the object that we're trying to access it on, this would be a really cryptic error because class A does have a hash foo. It just happens that we're not trying to access the same hash foo on it. We need to make a really descriptive error in this case. This error shows what we implemented, which tells you exactly that there is a case of shadowing here, where the shadowing declaration is, where the declaration of the hash foo that you intended to use was. The last phase of the compiler that I'm going to talk about is the transformers, and I'm not talking about Optimus Prime. The transformer phase is where we change the code before it's output to JavaScript. This allows us to remove things like type annotations and convert newer syntax to run on older JavaScript engines. So for example, if we're using arrow functions, we can convert those to be regular functions in a way that preserves the semantics. Or if we're using letter const bindings, it will also convert those down, extracting the body of this loop into a function that preserves the behavior. We can't just simply change this to var because this code is producing an array of functions that returns 0 through 9. Simply changing this to var would produce an array of functions that all return 10. To transform private fields, we have to first figure out how exactly we need to convert this example so that it runs in an older JavaScript engine. This example shows a person class with a money private field. We need to figure out how we can store the value of the amount of money that each person has without exposing it on the person objects themselves. This is important because you wouldn't want a derived class to be able to override the property for the amount of money. This is important because runtime privacy is a defining feature of private fields. If something is simply visible as a property on the object that was previously a private field, then we're not preserving the semantics. Additionally, there's the scoping rules that we talked about earlier related to derived classes, and that you can have multiple properties that have the same name in different base classes. So we need a way to associate each person with the amount of money that they have. One easy way to think about that is to just try to use a map. So let's try that first. If we use a map to store the amount of money that each person has, this is actually pretty close to what we want. Inside the constructor, we initialize the map by setting the this key to the amount of money, to the initial amount of money. This is equivalent to our original this.hash money equals initial money. We're just doing money.set on the map. Similarly, when we try to access the private field, we do money.get. This keeps the scoping rules that we want because money is just a variable that's scoped to the same scope as the class declaration. Additionally, it doesn't expose additional properties on the object that let you get at the private state. What's the problem with this, though? It turns out that the map stores every single person that's ever been created, and it doesn't automatically get cleaned up. So transforming a private field into code like this would leak memory everywhere. For every single person that's ever created, it could never be garbage collected. So how do we get around that? Instead, we use something called a weak map. A weak map functions much like a map, but it doesn't store references to the objects that are keys. Instead, it gives us the ability to associate data with an object without keeping it alive. This allows the person objects to be garbage collected and allows us to keep track of the amount of money that they have while they're still alive. Now, the only thing left is brand checks. The runtime semantics part of the spec tells us that if we try to access or set a private field on an object that doesn't have the private field defined, so it wasn't created with the constructor of the class that we're working with, then we have to throw a type error exception. This is what we refer to as a brand check. And in our transformation, we simply need to add a check to throw this error. We do this by wrapping access to the weak map in a function called class private field get and class private field set. In this, we just check if the weak map has an association to this object. And if it doesn't, we throw a type error. Let's talk about some of the interesting cases of the transformation. The first one I'm going to discuss is the postfix unary increment or decrement operators. This means the ++ operator that comes after a this.hash field or a ---- operator. When we write the transformation for this, we need to consider what the expression returns and how it mutates the field value. You may think that this is simple, but it's actually quite nuanced. There's one minor detail that's really easy to miss. You might think that we can simply store the existing value that was in this field, increment the field value by 1, and then return the existing value. This isn't quite right because it turns out that the ++ operator first coerces the value to a number. So if this.hash field stores a string, the return value of that expression will not be a string. It will be a number. So the first thing that we must do is coerce the field value to a number using the plus prefixed operator. Then we set the private field by incrementing that value by 1. Then we return that value. We wrap all of this up in a comma expression, which allows us to chain multiple expressions together and return a value at the end. The second case I'm going to talk about is pretty interesting as well. We're going to talk about how to transform the structuring assignment into a private field. If you're not familiar with the structuring assignment, this example here is essentially taking the first 3 values out of the array returned by the createArray function and setting them into the this.hash field, the A and the B bindings. When we transform this.hash field in this location, we can't simply transform this into a class private field get, which is essentially what our transformation would do as we've already discussed, because this is not an assignable target. We don't want to access the field. We want to call the class private field set, which would assign a value to this field. So we need to transform it in a way that keeps it as an assignable target. We need essentially the ability to call this class private field set when something gets assigned to the value. So how can we do that? We can call the class private field set function in the setter of an accessor property. We can transform this code using an accessor property that allows us to call the class private field set function while we're actually doing the destructuring. So the code will look something like this. We create an object that has a setter, and then we immediately access that setter. And that's what we replace the this.hash field with. Inside the setter, we can call our class private field set function, which changes the value of the field. This is a really crazy trick. It's so bizarre, and most people really would not write code like this. One of the things that we actually ran into when implementing this weird transformation is actually a bug in the V8 JavaScript engine used in Chrome and in Node.js. It's understandable that V8 didn't necessarily have 100% spec compliance here because sometimes bugs happen. But we were able to report this to them, and the V8 engineers were able to fix it in record time. Additionally, a new test case was added to the Test262 language test suite, which is used to evaluate JavaScript engines like V8 for spec compliance. I'd like to end this talk by acknowledging everybody who contributed to the TypeScript implementation of private fields. It was quite a collaborative effort. I'd also like to extend my thanks to the TypeScript team for helping us understand the compiler and facilitating a great contribution experience.